So, good afternoon, lecturer and friends. Our project is the large-scale uniaxial experiments on the creep behavior of rockfill material.
Rockfill material is a crucial element of rockfill dam because of easily available locally, inherent flexibility, capacity of absorbing large amount of seismic energy, and inexpensive material. A rockfill dam is a type of dam which comprises primarily compacted rockfill material, shaped much like bank or hill. Rockfill dam have two types. There are rockfill clay core dam and concrete face rockfill dam. In this project, we integrated the concrete face rockfill dam. We can call it CFRDS. Nowadays, CFRDS very popular because rockfill dam can build higher building and use rockfill material less than rockfill clay core dam at the same height. Moreover, unsuitable when earthquake happen because rockfill material have high shear state and is not have water pressure in dam. This is the structure of CFRDS. First of all, reinforced concrete face. The second, foundation. The third, rockfill core.
For the material we use in our experiment is limestone. Limestone is the material that has been widely used since the Stone Age in the building of the Pyramid of Giza. For creep is defined as the time-dependent increase in strain under a constant effective stress, which usually happens in the concrete face rockfill dam, and it is the most worrisome problem in the concrete face rockfill dam.
For this project, mainly to understand the behavior of rockfill dam during the creep with the influence of water and gradation subjected to the creep deformation. Limestone rock that using in this project form a mine in Kanchanaburi with the biggest size not exceed 60 millimeters. Using a lot modified audiometer testing with 3 different gradations in 3 different conditions as well. In this project, we expected to search for a suitable gradation curve and the deformation of the first filling of the dam. This graph shows the 3 gradations of the target design test. This table shows the target design for testing rockfill material in 3 different gradations and 3 different conditions.
These are the 5 main apparatus we use in our experiment, which is dial gauge, sieve, the large modified audiometer, the compaction plate, and the LDVT. For our procedure, to prepare the material, first we sieve the material using 6 different sizes of sieve, the 2.5, 1.5, 3/4, 3/8, sieve number 4, and sieve number 10 respectively. Then we wash the material and left to dry. After that, the soil is mixed into 3 different gradations. To compact the sample, we compact the sample into 3 layers with the compaction plate and the compaction hammer. To prepare for the audiometer test, first we carry out by putting the mold with the rock sample inside onto the compaction machine and cover it with the lid to expand the loading area. Then we place 3 dial gauge on the lid 120 degrees apart from each other. After that, we apply the load. The test starts by inserting the load 50 kilonewton onto the rock sample and maintain it for 2 hours. Then we increase the load every day to 125, 250, 500, 1000, and 2000 kilonewtons respectively. For the data recording, we mainly focus on 2 data, the load and the deformation. To record the load, we using the digital display to record the load and the LVDT to record the deformation of the samples. After finishing the test, we measure the fracture of rock by performing sieve analysis to check for the crashability.
For our result, this page will show the graph received from data recording. From figure 1 is the relationship between load and time graph, which obtained from the digital display, and the figure 2 is the relationship between displacement and time graph. The displacement is received from the LDVT. For this page, the graph illustrates the change of gradation between before test and after test.
The result from test can plot in the stress-strain graph as shown in the slide. As you can see, the graph didn't curve as the typical one because of the device that collects the data can correct data in 5-minute interval. That make this graph show the secant and tangent modulus instead of the curve. And for the slope of this graph can calculate the Young modulus. We got 582.319 megapascal, but in this case may not represent the real property of material. For the test, we focus on the creep behavior, but as you can see in the graph, the relaxation is happened during the test clearly more than the creep. So we will present about the relaxation that happened during the test. The relaxation will happen when the stress is decreased but strain is still constant, and creep will happen when the stress is constant but strain is decreasing during the time period. For all the 5 sections, we can see the graph rising from one point to one point that cause the relaxation and creep of stress and strain. And then the graph rising to the one point, the relaxation is happened. And then the graph is decreasing that show the relaxation of stress and strain. The graph represents the relaxation rate and time. As you can see, the relaxation rate happens in 5 different rates according to the stress and strain behavior.
For the compressibility index and the long-term compressibility, we calculate both of the parameters using the equations as you can see from the slide and plot the graph between both of the parameters. From the graph, we find the ratio to be 0.09, which is close to the upper ratio found by Alonso and Oldcap 2007, which is 0.05. In conclusion, the creep and the rockfill material can be successfully determined, and the behavior of rockfill material during creep can be determined from the relationship between stress and strain. The point that creep happen can be located by using the relationship between stress and strain. With the appropriate interpolation set up, the ability to predict the critical condition on the real structure will be achieved.
The relationship between stress and strain or load influence that the relaxation occurs when the applied load was unloaded after a certain time, which could have been computed by computation, and the compressibility index and long-term compressibility can be found through loading by record the loading force and time, which then used to calculate the compressibility index and long-term compressibility ratio. Second effect on rockfill behavior can be achieved through well-designed method with its compaction and calculate gradation. This opens the possibility of quantified scale effect in rockfill.
For the suggestion in further study, first of all, the load should be automatic, so we can control the load, and the data will be more accurate than the manual one. The second is the compaction equipment for the rockfill material should be provided. And the last one is when finished the test, should be a proper equipment for remove the material for safety.
Thank you for your attention.